Section 8.4, electronegativity and polarity. So we're going to talk a little bit about the idea of charge in a chemical bond. So let's begin by considering an ionic bond. The ionic bond is made of charged particles. So for example, we might have a sodium ion and we might have a chloride ion, right? Two charged particles. So what happens is when the sodium ion combines with a chloride ion, we have a bond that is considered ionic, meaning that there are charged particles that are attracted to each other merely by the fact that they are charged. They have opposite charges. It's just a positive charge attracted to a negative charge, often referred to as an electrostatic attraction. And if you recall, we said that the energy of attraction is, not equal to, proportional to the negative of the amount of positive charge times the amount of negative charge divided by the distance between those charges. So this would be the distance here. I'm measuring from the center of each ion. Okay? That's what we would call an ionic bond. Now, we also have covalent bonds. So these are neutral atoms, right? These are neutral atoms or particles. So for example, we might have a hydrogen atom bonded to another hydrogen atom. And those two electrons are shared, but they're shared equally. I'll put in parentheses equally, right? The two electrons, if you recall, the two electrons that are in that molecule are shared by the two nuclei, by the two hydrogen nuclei. So it's what we would call a covalent bond, okay? In fact, we might call it a pure covalent bond because we would claim that those two electrons are shared just perfectly equally by the two atoms. But sometimes we have molecules, or we have bonds in any case, where the electrons are not shared equally. And we call those polar covalent bonds. So these are unequally shared electrons by two or more atoms. I'll just say two atoms. Could be by more than two, but at least by two. Okay? So what we have then are really three different possibilities. We have the case where the only attraction is due to the oppositeness of the charges, right? The sodium ion is positively charged and the chloride is negatively charged. That's called an ionic bond. Then we have the other opposite side of that, which is with the electrons are completely shared equally, and we call that a covalent bond. But it turns out we can also have in between, and we call that a polar covalent bond. Okay? So taking a look at this little chart down here at the bottom, if the two atoms, atom M and atom X, share the electrons equally, we call that a pure covalent bond. Neutral atoms held together by equally shared electrons. Then we have the other extreme, all the way over to the right. M plus X minus. That's an ionic bond. Oppositely charged ions held together by electrostatic attraction. But now we are going to claim we can have something in between. M delta plus X delta minus. A polar covalent bond. A partially charged atoms held together by unequally shared electrons. What's happening here is there's actually two forms of attraction occurring here. One is the attraction due to having differences in charges, and the other thing is the sharing of electrons. So two attractions are occurring for the polar covalent bond. Now, we can represent that unequal sharing by considering something called polarity. And what I'm going to do is I'm going to show you this picture down here. We have in this picture an example of a pure covalent bond. And this diagram shows, it's called an electron density map. It shows red where the electron density is, meaning that in the hydrogen molecule, the two electrons are located between the two nuclei. So just so you know, the nucleus of the hydrogen, for the first hydrogen atom might be right there, and the nucleus for the second hydrogen atom might be right there. Okay? So what that shows is that the density of the electrons is in between those two nuclei. That's the covalent bond, purely covalent bond. In the case of hydrogen fluoride, HF, again, the nucleus might be right here, and the other nucleus might be right there. Oops. There we go. I'll go up a little bit. Okay. Look where the electron density is located. It's primarily over here on the right by the fluorine, which tells us that the electrons are not shared equally by the hydrogen and the fluorine. They're more closely held by the fluorine. Where it's green, there's still some electron density. Where it's blue, there's very little electron density. So here, there's some green in between. So there's a little bit of covalency there, but it's mostly on the right, so it's somewhat ionic. So this is what we would call a polar covalent bond. And then all the way over to the right is sodium fluoride. We know that's an ionic bond, right? Look where all the red is. It's all over here by the fluorine, by the fluoride. Okay? That means that the electrons are not being shared at all. In fact, even the green is over by the fluorine. So this is what we would call an ionic bond. Unequal sharing of the electrons. So between hydrogen and fluorine, there's unequal sharing. Between sodium and fluorine is so unequal, there's like no sharing going on at all. So that leads us into something, a way of describing this, something called electronegativity. Electronegativity is a measure. It's something that we can tabulate. It is a measure of the tendency of an atom to pull electrons toward itself and away from the other atom that it's forming a bond with. So let me bring this up here so you can see it. Electronegativity. Okay? So take a look at the periodic table here. This is a chart of the electronegativity. Okay, let me just put in a little bit of editing here. There we go. If you take a look at this chart, what you'll see is that each atom, each element has an assigned value of electronegativity. So for example, the value for hydrogen is 2.1. The value for fluorine is 4.0. Each of these values is something that's been measured and calculated and tabulated here. And so first you want to look at some of the patterns. Take a look at the numbers. See how the numbers generally are a little under 1 up to 4. The highest value on the table is 4. Fluorine, which is element number 9, all the way in the top right corner, has the highest value. We would say that fluorine has the largest or greatest electronegativity of all the elements in the table. The second highest value is oxygen at 3.5. The third highest value is shared between nitrogen, chlorine, and krypton at 3.0. The values of the metals vary quite a bit. So for example, cesium in the bottom left corner is 0.7. That's the pretty small value on the chart. It's the smallest value on the chart completely. But some metals are higher. So for example, aluminum is 1.5. Let's see if there's any others. Zinc is copper is 1.9. Palladium, rhodium, and ruthenium in the transition metals, second row, is 2.2. So metals vary quite a bit, from under 1 all the way up into the 2s. The non-metals in blue tend to have the largest values. The metals tend to have smaller values. Okay? One pattern is as you move from left to right, the electronegativity increases from left to right. As you go from bottom to top, it increases as well. So that leads us to the highest values in the top right and the lowest values in the bottom left. You should memorize those two patterns. Increasing to the right toward the nonmetal, increasing up the periodic table toward the top. With the highest values, element 7, 8, 9, and 17 for chlorine. Okay? So those are electronegativity values. Now, how do we use electronegativity values? Oh, actually, before I even go through that, let me show you. I should have one more chart here. I guess thought it was here. I'm sorry. There we go. There's one more chart here I want to show you, which is this repeating pattern in the periodic table. So if you take a look at this chart, what it shows is that the electronegativity, starting at lithium, which is atomic number 3, increases as you go across the periodic table up to fluorine, and you get to 4.0. So that first curve that goes from left to right, it starts at lithium and goes up to fluorine, the electronegativity increases. But then the next element is sodium, element number 11, and that's a metal, so it pops back down and increases again up to chlorine. And then the next element is potassium, which is a metal, so it pops back down. And then it increases, gets more complicated with the transition metals, and then through zinc, and then goes back up, following the same pattern it had earlier with the nonmetals, maxing out at bromine. Okay, so that's a pattern that's there. Okay, now what we can do with electronegativity is we can use it to come back to this categories that we have here of bonds: pure covalent, polar covalent, and ionic bonds. And so here's the criteria that we're going to use. What we're going to do is we're going to use the criteria. Okay, let me get rid of this. There we go. We're going to use the criteria. Oops. Let me just get rid of some of this. There we go. We've got some room here. That if in a bond between two atoms, the difference in I'm sorry, let me spell this correctly. Electronegativity values is 0 to 0.4, 0.5 to 1.9, 2.0 or greater. We're going to call this a covalent bond. We're going to call it a polar covalent bond. And we're going to call it an ionic bond. Okay, those are our three categories there. 0 to 0.4 is covalent, 0.5 to 1.9 is polar covalent, and 2.0 or greater is an ionic bond. So let me show you what I mean by that. Suppose we had NaF, and we wanted to know what type of bond is the predominant bonding that takes place in sodium fluoride. Is it covalent, polar covalent, or ionic? We would look up the values of the electronegativities. For sodium, it's 0.9, and for fluorine is 4.0. We then do a calculation of the difference. I'll call it delta for difference. It doesn't matter which one you put first, which one you put second. I'm going to put the larger minus the smaller. And you get 3.1. That difference is in this range here. It's 2 or greater. So based on that criteria, we would claim that this is an ionic bond. The ionic bonding is the dominant attraction between the atoms in that molecule, in that substance. Okay? Now, the larger the electronegativity value, what that tells you is that that's the atom that's going to have the negative charge in this in this ionic bond. So the fluoride will have the negative charge. I'm going to use the Greek letter delta to represent small negative charge. And then the one with the smaller electronegativity, that's the one that's going to have the small positive charge here. Okay? Now, how big are those charges? Well, for sodium, that small positive charge is actually pretty close to 1 charge, 1 unit. And for fluorine, it's pretty close to -1 units. Okay? Let's try a different one. Let's say that we have pH as our bond. Phosphorus and hydrogen. We look up the electronegativity values for each atom. And then we calculate the difference. Oh, look, they're the same, right? So that difference is 0. So we would call this a pure covalent bond. Pure sharing. No charges in that substance. And then finally, let's say that we have oxygen bonded to a hydrogen. We look those electronegativity values up, and we look at the difference. Take the larger one, subtract the smaller one. 1.4. So that is definitely polar covalent, right? That's a polar covalent bond. So that means there's a negative charge on the one that has the higher electronegativity and a positive charge on the atom that has the smaller electronegativity. So delta plus, or delta minus I should say, and delta plus, these are ways of representing the charge on the atom. Okay? So what's happening is the OH bonding, the bonding that takes place in OH is such that the unequal sharing that there's more electron density on the oxygen. These two electrons, which we're just representing as a simple little line, are actually more concentrated on the oxygen and less concentrated on the hydrogen, resulting in a negative charge here and a positive charge there. Okay? There are more details of this. We can talk about dipole moments, partial charges, and percent ion character, which we'll talk about in a separate video.